Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. Today, inshallah, we'll continue talking about gradient descent and its modifications. And inshallah, from next lecture, we'll start to talk about how to compute gradients. I think we stopped here last time. We were talking about a problem with gradient descent. If we started from this point, if you remember the Gable model example, okay, and that's the loss function that we discussed. If we started from that point, the gradient descent will take the model to the global minimum. If we started from point 3, we will also reach the global minimum. But if we started from point 2, we will get stuck to a local minimum. Okay, so that's a problem with gradient descent that we will try to see how we can avoid with other methods to some extent. So this is a quick poll to make sure that you got the concept so far. A convex function has only one global minimum, only one local minimum, no local minima, no global minimum. Only one global minimum and no local minimum. Okay, and no local minimum. Right. Is it guaranteed to find the global minimum of the loss function using gradient descent? No, it's not guaranteed. Right. We can find the global minimum of the loss function using gradient descent. Never, or not guaranteed, or it depends on the starting point. The last two, right? It's not guaranteed to find the global minimum, and of course it depends on the starting point. Now we'll switch to modifications trying to address this problem. Okay, so what is the problem? Yeah, so not to stuck in a local minimum, right? Okay, so there are three methods that inshallah we'll try to cover and see what the concepts are. The first one is called stochastic gradient descent. So what is the main idea of stochastic gradient descent? The main idea is to add some noise or randomness to the gradient. Okay, hoping that doing so will get us out of the region of a local minimum. Okay, right. What does that mean? Adding noise here means that instead of computing the loss over the entire training data, we will only compute the loss over a small subset of it. We call it a batch or mini batch. Okay, so let's say that we have thousands or millions of training examples. We will not compute the gradient over all of them when we make the changes of the model. We will only compute the gradient over a very small subset of them. We call it a mini batch. Okay, right. Let me show you the difference. This is the gradient descent, right? Where is the gradient? This part, right? So this part is the gradient, right? It's taken over all training examples. This summation is over all training examples, right? Right? So that means that we are computing the gradient. So Li is the loss, or the partial derivative of Li with respect to phi is the loss, is the gradient of the loss for a specific training example. Okay, and we are doing that over all training examples. Okay, that means that for gradient descent, we have to compute all of that. We have to compute all of that. Then we make the change in the model. Okay, we have to do it over all training examples, computing the gradient for all of them, and then make the change in the model. That's the original gradient descent algorithm. Now, with stochastic gradient descent, we have this one. Can you see the difference here? Okay, there is one only difference here. What is the difference? The difference is here. Okay, the difference is here. The summation, instead of being over the entire training data set, it is only now over a batch. Okay, over a batch. Batch means it's a subset, small sample of the entire training data. Usually it's in tens. It's 32, 16, 64, something like that. Okay, very few, a small subset sample of the training data. And this is what we call stochastic gradient descent. Okay, so you see the difference now? Instead of computing the gradient over the entire training data, we computed only over one batch. And then, of course, we have another batch, compute the gradient. So here, the iterations will not be over the entire training data. Okay, every iteration here is on one batch. So we compute the gradient over one batch, we make the change. And then we take another batch, compute the gradient, make the change. Then take a third batch, compute the gradient, make the change. In the original gradient descent, we compute the gradient over all the training data and make a change. And then do it again and make a change. And then do it the third time, make a change. Okay? So the batch here is, again, it's a random sample. Usually it is without replacement. Okay, so we take a subset of the of the training set, do the modification, take another subset, take a third subset, until we take the entire training set. We call that an epoch. So when we fully go through the training data, this is called an epoch. Okay, so we can the training data can have maybe thousands of batches. After we are done with all batches of the training data, we go through them again. Okay, every one pass over the entire training data is called an epoch. Okay, any questions? Yes. Yes, eventually, yes, of course. We will go through all of them eventually, but the difference is when to do the change in the model based on the gradient over all of them at once, or we do the change based on small batches. And we'll see how that will make a difference. Yes. 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 It, okay. It can happen. It can happen. It can happen. And we'll see what will happen. Okay. But doing that, the expected gradient, the expected direction of the gradient is the original gradient. Okay. But it is taken over different steps. We'll see the effect of that. You still have a question? Without repetition. Yani the batches, usually we take the batches to be disjoint. Okay. Any other questions? Right. Let's see the effect of that. On the left side, you will see gradient descent. This is what we saw in the beginning of the lecture. Okay. If we start from point 3 or point 1, we'll go to the global minimum. And if we start from point 2, we'll go to the local minimum. Now switching to the right side, this is stochastic gradient descent. Notice what is happening here. There are lots of zigzags, right? Okay. Why is that? Because of the noise. Where does the noise come from, by the way? Yeah. Why? Yeah, because we are taking, instead of taking the actual gradient of the loss function, we are taking like an approximated gradient, only computed based on small subset of the examples, of the training examples. Okay, so it's not actually the gradient of the original loss function. Okay, so you will see that based on the batch, the gradient sometimes might be this way, and then next time would be this way, and then third time would be this way, and so on. Okay, so you will see that it is a zigzag like that. But it happened that because of this randomness, in this case, we managed to go to the global minimum. Okay, we escaped the wrong value here. Of course, this is possible, but it's not again guaranteed. It's not guaranteed, but there is a chance that we will escape the area of the local minimum and go to the global minimum. Okay, yes. If we increase the batch size, yes, we'll go back to the original one. Okay, as we increase the batch size, it's like we are going to the original gradient descent, of course. There will be some more zigzags, right? So actually, batch size, we'll talk about it, I think, later, can be considered as a hyperparameter. So you can tune the batch size. Okay, but that's the main idea. Any other questions? Okay. Right. Let me show you another view of that. Okay. Look at the top left corner here. You see this? This is the original loss function that we saw before. Okay. And assume that the model that we reached is this point. When we zoom in, it's this point. Okay. Right. What are these all directions? Remember, in stochastic gradient descent, we take a batch and compute the gradient and go in the reverse direction of that gradient, right? That's what happens in gradient descent. Right. How many possibilities we have if we take a random batch? So many, right? Because the batch size even is small. Taking a small subset from a very large subset, we have so many possibilities, right? Each one has a gradient. So it can be in that direction, it can be in that direction, it can be in that direction, right? There are so many directions, possible directions, that the model can take based on different batches, right? That's exactly what you can see in the other figures. Okay, yeah, look at now this figure, the top right figure. Okay, forget about this one now. Okay, still we have the same model at the same point, but the figure is different, right? You notice that this figure is different than that. Okay, this is actually the original loss function. This one on the right is the loss function based on the batch that we are taking here, which is this 3 points. Here the batch size is 3. Okay, so when we take this batch, actually we are using a different loss function. Okay, the loss function that is based on only these 3 points, only these 3 examples. Okay, and thus the shape and the look of the loss function, of course, will be different. But still, we will be going in the reverse direction of the gradient of what? Of which loss function? Of the batch loss function. Of the batch loss function. Okay, so in this case, you can see that the gradient is going this way, and so the movement will go in the reverse direction. Okay, so this is based on this specific loss function. And you can see here the dotted curve is the original model, and the solid one is the one after we do the change. And you can see that it is getting closer to the point, to the 3 points, right? Because it is minimizing the loss function that is defined over these 3 points. So we are minimizing the error here. Okay, so it moved towards these 3 points. Same with the other two. If we change the batch, okay, here, let's take this one. These are 3 different points. That's another batch. We will compute also the gradient, but the gradient of this loss function now, and move in the reverse direction. Same here. Same here. Okay, but here the loss function is completely different. Okay, the gradient is this way because the increasing of the loss is this way, so the movement will be in the reverse direction. And this one in particular is very interesting. Look at the movement, the direction that the model will change to here. It is the opposite of the direction that should be moved from the original loss function. Okay, so actually the textbook says a nice statement here. It says we go downhill but uphill. Okay, we went downhill with respect to the loss function of the batch. So we are minimizing in the space of the loss function of that batch, but actually we are going uphill, it seems, based on the original loss function, which is based on the entire training set. Okay, did you get the point here? So the point here is that based on the batch, we are actually minimizing a different loss function. Okay, so we might go in a good direction with respect to the original, or a bad direction with respect to the original direction. But eventually, because we are doing that over the entire training data, okay, eventually the expected direction is the original direction. Okay, so we hope that with this randomness, with this approximation of the loss function, we might get out of the value of the local minimum. Okay, and that's what happened actually here. Okay, question, yes. So you said the loss function is yes. That means that we can have batches of different sizes. Usually it's fixed size. Yeah, theoretically yes, you can change the size, but what I see always is the batch size is fixed. Okay, but I'm not sure, depending on how you will change it. That will, of course, have a negative effect on the computations, because fixing the batch size will make it much easier to do the computation, actually. But theoretically, yes, you can. I don't see a reason why we cannot change the batch size, but I don't know if that will have a good effect or not. No, with any batch, the loss function will change. Whether it is small or big, it is different than the original one that is defined on all the training set. It's different from the original one. Yes. For each batch, we were using the same loss function. No, the loss function is defined based on the loss function is function of the input of the training examples. Okay, so if I change it, the batches, because the batches here are disjoint. Okay, so but overall the expected, of course, will be the original one. Yeah. Okay. Is that clear? Any questions? Okay. Type. Stochastic gradient descent has so many nice properties, actually. The first one that we just mentioned is that it might escape the local minimum. Okay, and that's the most important one. It also, while it adds noise, but still the updates are logical, right? Because they are based on the training data. We are not using any other data. It is part of the training data. So the updates still have some meaning, okay, but based on small subset. And eventually, as I said, it will use the entire data, okay, and it uses the entire data equally, okay, especially if the batch size is fixed, okay. So it uses all the data equally eventually. It is less computationally expensive. Why is that? You mean faster? Maybe, but actually that's not the main reason here. The main reason here is that we are computing the gradient over small subset of examples and then do the change. The other one, we compute the gradient over all of them before we do the change. Yeah. We are changing so much, but in every step of making an update to the model, it is much faster. Right? Right. And in practice, actually, it was found experimentally that stochastic gradient descent can find models that can generalize better than gradient descent. Okay. Right. In practice, also, usually stochastic gradient descent is done with what we call learning rate schedule. So far, we said that the learning rate is fixed, right? Remember alpha? Okay. So far we said that it is fixed, but that's not always the case. With stochastic gradient descent, usually we use a dynamically changing learning rate. We start with a large learning rate, and over time we make it smaller. What is the logic behind that? Why we are doing that? Initially, first of all, when we have a large learning rate, we make large large updates or small updates? Large updates, right? So in the beginning, we want to explore more. So we increase the learning rate. We want the learning rate to be high, so that we make big jumps to explore the entire space. But then after some time, we want to do fine tuning. We want to be more precise. Okay, so we want the learning rate to be smaller so that the changes will not be that big. Okay, so that's the idea here. Okay, so that's it with stochastic gradient descent as is. Now we will see that we can do two changes to, or at least two changes. Actually, we'll see three of them that will make it sometimes faster, sometimes more precise. The first one is called momentum. Okay, so what is momentum? With stochastic gradient descent, if we go back to the equation of stochastic gradient descent, the change with every batch depending only on the gradient of that batch, right? Yani we compute the gradient of that batch and then we make the change, right? It doesn't take into consideration any gradients of the other batches, right? It just starts from where we are, we compute the gradient, and then we move change the model, right? With momentum, we change this. We actually take into consideration not only the gradient of the current batch, but also the gradients of all previous ones. Okay? So we don't forget the history. We take the history of the gradients into consideration. And also we take the gradient of the current batch. How is that? It is done by a weighted sum. So we give a weight to the gradient of the current batch and another weight to the gradient that we made in the previous, that we reached at the previous batch. Okay, so look at the first equation here. M is the gradient that we will actually use in the change. So in the second equation, this is the standard gradient descent, right? Okay, except that here instead of the actual gradient, we call it mt plus 1. Mt plus 1 is the actual gradient that we will use for iteration t plus 1. Okay, now how do we compute mt plus 1? Where's the gradient of the current batch? That's the summation, right? That's the summation. Okay, so that's the current gradient. We'll call it current gradient for now. Current gradient means the gradient of the current batch. Okay, we will multiply it by a factor that is between 0 and 1. Beta actually is between 0 and 1. Beta is a parameter here. Okay, and usually it is high value. So let's say مثلا beta is 0.9. Okay, so we will multiply the current gradient by 0.1 and add it to 0.9 of the gradient that we used with the previous batch, which is mt. So this is a weighted sum. We give some attention to the gradient of the current batch and also another attention, some actually higher, to the previous one. Okay, so that means that we trust the history more usually. Okay, type, is it actually only the gradient of the previous batch? Notice that I didn't say the gradient of the previous batch. I said the gradient that we used in the previous batch. Okay, the gradient that we used in the previous step. Okay, because this is recursive, by the way. If you look at it, it is recursive. Okay, it's 10% of the current gradient plus 90% of the gradient that we reached in the previous step. So if we expand it, you will see what I'm saying here. Let's try to expand it. Okay, let's say that we start from the first step. Before we do the first iteration, we have m0. Okay, and m0 is 0. That's the beginning, right? We don't have any gradients. Then let's compute m1. What is m1? Let's say that beta is okay. Let's use beta. Okay, we'll not make it a specific number. Let's use beta. So m1 is beta m0 plus 1 minus beta This is, let's call it the gradient at batch 1, G1. Okay, with me? Type. Now let's compute M2. Beta M1, which is what? Which is this entire thing, right? So if we multiply beta by this, that will be beta square M0 plus beta 1 minus beta G1, right? All of that plus 1 minus beta G2, right? Right? Let's do it one more time. M3, what is M3? It's beta multiplied by all of that, right? So it will be beta cube M0 plus beta square 1 minus beta G1 plus 1 minus beta, beta 1 minus beta G2 plus 1 minus beta G3. So what's going on here? It's actually we are taking into consideration all the gradients of the history. Okay, but with different weights. Okay, and if you notice the weight as we go back in history, the weight increases or decreases? No, it decreases actually. Beta is less than 1. So we are multiplying by a number that is less than 1. Okay, every time. Okay, so the oldest one is multiplied by beta cube. The more recent one to it, beta square times 1 minus beta. Okay, and then beta times 1 minus beta. So every time we multiply the history by beta and the present by 1 minus beta. Okay, so the very old one will be multiplied multiple times, right? So it will get smaller and smaller. The weight of it will get smaller and smaller. Okay, so that means that we favor, of course, the gradients of the recent batches. Okay, yes. No, you mean the momentum or the stochastic? Because this is not stochastic. This is a modification to the stochastic gradient descent. Yeah. So okay. So with gradient descent, with the original gradient descent, we are computing the gradient over the entire training data. خلاص? With stochastic gradient descent, we are doing the gradient only on one batch at a time. So we are doing the gradient with one batch, make the change. Gradient of another batch, make the change. Now with the momentum, what are we doing? Actually, you are taking an infinite weighted sum of all gradients of the previous batches. Okay? And if we are in iteration number 100, if we are now using batch number 100, we are using the gradient of all previous batches plus the gradient of the current batch. Why is it lowest? We don't know yet, but you will see the effect of doing that. Okay, this is a weighted sum. Because we are doing that, do you think that the changes that will be done will be very different from the previous one? Yani I'm at iteration 100. The change, the direction that I will take now, based on what you saw here in this slide, will be very different from the direction that I took in iteration 99. It will be a bit different, but not very different. Okay, so you will see the effect of that in the next slide. But let me now, do you have any question on this, or should I erase it now? I think this is clear, right? If you do that, of course, more than that, you see how this will go. So I can say that this is an infinite weighted sum of all previous gradients. Okay, from the very first gradient to the gradient of the current batch. Okay, now let's see the effect of that. On the left-hand side, we don't have any momentum. We are just using the gradient of one batch. with every step, okay, which is the current batch. And you can see if we started from this point, you can see how the path will go through. Okay, both, by the way, if we start from this or that, we will go to the global minimum. Okay, but look now, if we use the momentum, what happens? What do you notice? On the right side, we are using the momentum for both. Huh? It's much smoother. It's much smoother. Okay, which means what? Faster. Very good. Yes, faster. With less number of steps, we can go to the global minimum. Of course, this is again possibly. Okay, it's not again guaranteed. Okay, but at least instead of making very different changes with every batch, we are taking the history into consideration so that we don't divert much from what we learned. But the history is taking less weight over time. The very old gradients are decaying. The weight of them is decaying, actually exponentially decaying, and they were giving a higher weight to the recent ones. Yes. Okay, faster in terms of steps here. If you look at the two figures here, which one will take less steps to reach the global minimum? Yeah, the momentum one, because it's the path is straightforward, not straightforward, it's smoother at least. The other one, as you see here, it goes up and then goes down and then up again, right? So of course that's again not guaranteed to be like that, but in practice, yeah, it is much smoother, and in that case, it will be faster. Yes, faster to converge. Okay. Yes. It's more likely here with, you mean with stochastic or with uh, but with more random also you might get out. Yes. Not always, of course. Yani in practice, not always. Yeah, momentum is really better than the stochastic gradient descent. But of course, in both cases, it's not guaranteed that you will get to the global minimum. Okay, it. I can see your point. Now you are saying something like we are reducing the randomness now, right? To some extent, but reducing the randomness not because we are using the entire data set. Still, there is some randomness, but we a little bit controlled it. Okay, so that we can reach the global minimum in a faster in a less number of steps. Okay, of course these are hopes. Again, there's nothing guaranteed, nothing proved for sure that we will reach the global minimum. Yes, faster in less number of steps. It, you mean without momentum or with momentum? Even with momentum, by the way, don't forget that we are given higher attention to recent batches than old batches. Okay, so even if we diverge, there is still hope that, or there is still possibility that we will get back to where we should. Still, it is still somewhere in between. Okay, the original gradient descent is kind of an extreme because we are taking into consideration everything, and the stochastic one is only on one batch. This is somewhere in between. Okay, it's giving some weight to the current batch, but also some weight to the history. I need to. Okay. Okay, good question. Why don't we take 50%, 50%? Actually, this is a hyperparameter. You can tune it. Okay. we'll talk about tuning hyperparameters later. Okay, I mean you can change it and see which one is good for your problem. Okay, so I cannot tell if 50% is bad or not, but usually if you will not change it, you set it to a high value so that you don't make big changes. Now if you make it a small value, what happens here? If beta is small, okay, then this number is big, right? Okay, so you give very high weight to the current batch, so you are back to stochastic. Okay, you are back to the stochastic one. Okay, yes, it depends on the gradient, but I'm saying based on the weights. If you give high weight to the current batch, you are kind of back to stochastic gradient descent. Okay, the last one that we will discuss now is Nesterov accelerated momentum. So this is a change over the momentum idea. Okay, what is the idea here? The momentum is like a direction based on all the history, right? So it's like the prediction. If now I am at one point in one iteration, the direction that I will take next, will it be very different from the history? No, right? It will be a bit different, but not very different from the history. So I can actually think of the history as a prediction for the next step, right? So Nesterov actually is taking this a step ahead. It says that this is the momentum, but now with this accelerated momentum, we change taking the gradient at the current model to taking the gradient at the predicted model. So look at the difference between this and that. What's the difference? This is the gradient over one batch, right? This is over batch T. Okay? That's the current gradient, right? The gradient of the current batch. Now, look at this. What is this? What is phi T? That's the model that we reached in the previous iteration, right? This is iteration T plus 1. So phi T is the current model before we change it. Okay? Now, look at the model at which we compute the gradient here. So here we compute the gradient at the current model. Okay? Here we compute the gradient at the predicted model if we take the momentum direction. So this is phi t minus alpha mt is like, this is the new model if we use the gradient descent, right? So it's like we are computing the gradient at the future point. So we are making look ahead of the future and compute the gradient there. Let me show you what does that mean exactly. With the momentum, not Nesterov, with the momentum, okay? Let's say that we are in this position of the model, that the model is at that point now. Okay, what does that mean, the model at that point? That's based on the values of the parameters, okay? Type. With the momentum, we take two things into consideration, right? The gradient of the current batch, which is the red one here. So that's the gradient of the current batch. And the momentum also, direction, which is the green one. We take both into consideration. For simplicity, let's say that it's 50-50. Okay, so we take 50 of the gradient step and 50 of the momentum, or actually, let's assume that we just add them, okay, equally. So from linear algebra, when we add two vectors, so we are here, right? If we go through this direction plus the momentum direction, we will reach this point, right? That's from linear algebra, right? Okay, going this way, and then this direction of the momentum, we go to this point. That's the momentum. Now with Nesterov, what's the change? We are in this point, right? Where is the direction of the momentum? The green one. Okay, so if we take the momentum direction, we will reach this point. If we will only take the momentum direction, we reach this point. What is the gradient at this point? This is this one. This one. That's the direction, the gradient at that point. That's the gradient at the new batch. Okay? Now this is, look at this, this is different than this one, right? This one is straight, this one is not. This is the gradient at the current model, this is the gradient at the predicted model if we take the momentum direction. Okay, so this is like we are looking ahead one step and see what the momentum will take us, and then compute the gradient there and take it into consideration when we make that change. Now we make the change, this plus this and this, okay, plus this, we will reach this point, which is different than this point. Okay, so this is called look ahead gradient step. Okay, it's different than the original, and it might also take us to a different solution. Okay, same here. If you look at it at the loss function, okay, that's the same idea that that we saw in the previous slide, but on the loss function that we saw in the beginning of the lecture. Okay, we are at point 1, that's the current model, and this dotted line is the direction of the momentum. With momentum only, we will take the addition of the momentum plus the current gradient, which is this one. So we'll go this way, and then this way we reach point number 3. With the momentum, we go through the momentum and then take the gradient at that point, which is this white one. So we reach point number 5. So we can reach 2 different models here. Okay, with Nesterov, we reach another model than the one that we can reach with the momentum. Okay, so this is like looking at the future one step, and that might be faster to reach the global minimum. Any questions on that? Okay, inshallah, we'll continue with the last one, which is Adam optimization, which is the most widely used currently, and then inshallah we'll switch to how to compute gradients. Okay, Assalamu alaikum wa rahmatullahi wa barakatuh.